Hello, everyone. My name is Frank Krueger. It is my pleasure to be presenting to you using your programming skills to make 3D objects with OpenJSCAD. It's a long title. Apologize for the wordiness. Or maybe just 3D objects with OpenJSCAD to start with. A little bit about myself. I am a software developer. I write mobile apps, mostly on iOS, but I'm also a very avid robot enthusiast and IoT enthusiast and embedded programmer enthusiast. Let's see. Here's one of my little robots. It's very cute. It has two legs, lots of servos, and doesn't work at all. But it's cute, and I like its little body here. Here's another one of my little robots. This one is supposed to balance, but it's crashed a lot and its face is broken. But as you can see, it's a lot of electronics with 3D printed enclosures. Robots are just fancy enclosures for electronics. So I'm happy to be presenting to you how to do all of that with OpenJSCAD. I fell in love with OpenJSCAD because I found that I don't have much patience with normal CAD programs, but I'm a programmer and I have programming skills, and it turns out you can use your programming skills to create 3D objects, and that's when I fell in love. And I hope that through this presentation I can help you fall a little bit in love with it too. So we have an agenda. First, I'm going to introduce the concepts of OpenJSCAD and using code to make 3D objects. Then I'm going to do a demo and actually build an enclosure in real time. Cross your fingers, wish me luck that I can go very fast. And then hopefully if there's time left, I can do some tips and tricks to help you along your way. Basically lessons I've learned over time. So let's get started. So the whole premise here is we're going to create 3D objects from functions. If I want a sphere, I call a function called sphere and pass the radius to it. If I want a cube, I call a function called cube and pass a size to it. I can even do crazy things like subtract objects from each other. So here I have a sphere, and I took a cube and I just subtracted the cube from it. I removed it from the sphere, and that was done using a difference function. But the premise is still simple, that functions are 3D objects. And the thing that makes all of that magic work is OpenJSCAD.org. It is an open source web app. It's actually also a library. You can use it in library form, but mostly it's a web app. And it's free, and you can just point your browser to openjscad.org to get started. But don't do it just yet. I'm going to walk you through some basics first. So this is the basic UI of OpenJSCAD. On the left, you have a preview rendering of your object. On your right, up there, I think, is a bunch of code. And there's a few things we should observe here. Number one, the JS stands for JavaScript. The code we're using is JavaScript. If you don't know JavaScript, it's not too bad of a language to learn. A little bit wordy here and there, but it's all good. I hope these examples, there's going to be so many examples throughout this presentation. I hope that you'll be able to pick it up pretty quickly. The important thing here is that we create a function called main. Whenever OpenJSCAD runs, it's going to take whatever object you return from main and render that. That's your 3D object that you're creating. Here, I'm returning a sphere from main, and so OpenJSCAD shows that sphere. Oops, went a little too far. Oh, getting ahead of myself. Quite a little simple change. I can change from sphere to cube, and instead of getting a sphere, I get a cube. That's the basic premise. We write JavaScript code and just start returning objects. The difference looks the same as I showed in the previous example, but here's the full version in all the JavaScript glory. We have the difference function right up there, and we are taking a sphere and removing a cube from it to get the object on the left. In OpenJSCAD, we have primitives. These are the fundamental 3D objects that we can start with to create our own designs. We're not limited to these because we're using a programming language and we're going to make complex designs out of these, but these are the basics, the building blocks. If you're in a Minecraft world, you know you can do a lot with just a cube, but we have a cube and a bunch of other things. So what do we have? We have a cube, which can have different sizes. We have a sphere. We have cylinders. Those are your basic 3D objects that you can do pretty much everything with. We have a torus, which is a donut. If your design needs a donut, that's great. I've yet to make a design or a robot that really needs a donut. You know, that's not true. That's not true. Let me show. I used a torus to create the bottom of this robot, to create this axle here. So you have these wheels. This donut here, this is a donut that I've scaled and resized to make an axle for the robot. So I guess torus is useful, just not as useful as cube. Right, so we had the torus. We also have polyhedron if you want to put a whole mesh in there. It's not too easy to use, but it's technically there. There's also text. Also not the easiest thing to use, but it's there. Now, from those primitives, we can manipulate them in a few ways. These are called transformations. We have translate, which is how you can move objects side to side, up and down, forward and back. It's your primary movements. We have rotate, rotate X, rotate Y, rotate around arbitrary axes, all the different rotations you could ever want, and there's scaling. These are your basic 3D transformations that you'll ever want to apply. Mostly you're going to be using translate and rotate. Scale doesn't come up that often. And finally, probably the most powerful feature, and the feature you're going to use the most, and the feature that you're going to have to think about a little to use, are called the operations. These are sometimes referred to as constructive solid geometry, and it's ways to combine multiple objects into one object. The most common one that you're going to use is called union, and that is I have multiple objects, or just A and B, two objects, and the union of them is those two objects. Everything that comprised the two before, unite them. Difference is what we showed before about subtracting an object from another object. So you're taking a byte out of it. And you can see that in the diagram a little bit. These diagrams are always a little tricky to think about, but I like to keep that image of the sphere with the cube bitten out of it. A little Pac-Man image to remember how difference works. Intersection is a weird one that I rarely use, but sometimes it's useful, is to take multiple objects and only return the part that they all have in common. It has its uses, but you'll see I rarely use it. But here's the big one. We have the power of an entire programming language, JavaScript, at our disposal. That means we can do calculations. That means we can make loops and recursion and all of our programming techniques. That means we can make things conditional. So parameterization of our parts. Maybe you have some debug versions of the parts. Maybe you just want to play around with some if statements. We have all of that. And most importantly, we have functions. Functions enable a variety of things that you can do. You can do what I said from the very beginning, custom 3D objects. That's our main use of functions. But we can do custom transformations and custom operations by passing functions to each other, higher order operations. We can parameterize our objects so that we're not just designing one servo, but multiple kinds of servos. We can use functions to create a whole family of parts, not just one part. Also, functions are used for abstraction so that we don't have to always think about the details. We can build up black boxes and black boxes that use black boxes and black boxes that use those black boxes so that we can hide information, so that we can build complex parts without getting lost in that forest of complex parts. And just to put it out there, it's a programming language that can access data. So you could query text files for information. You could query servers for information. You can build parts that are generative, that generate themselves. Wonderful things you can do with a programming language and functions. Really, it's up to you. Right, so that is the high-level abstract overview of everything. What I want to do now is get concrete. I want to dive into a demo so that we can all see what I'm talking about and why I like it so much. I have a lot to show, and I'm going to do a lot of typing, so wish me luck. I'm a little nervous. But first, a high-level overview of what I want to do. When I think about modeling an enclosure, I think about first modeling the exterior shape of the thing. In the case of the robot, it's the shape of the robot and whatever mount points I need to motors and things like that. And then I think about the cavity. I want to hollow out that shape. Multiple reasons. You know, you might want a small cavity or a big cavity, but mostly just to save printer plastic and time and all that stuff. So you want to carve something out of that. And then I want to make sure that I have mount points for all the electronics or whatever else that I need to put inside of this enclosure so that I can bolt everything down mechanically with screws and bolts and all that kind of stuff. So you take a shape, subtract a cavity from it, add mount points, and all of that gives you an enclosure in the end. That's the goal. Oops, getting ahead. So it is demo time. Let's talk about modeling an enclosure. Here is a picture of what I want to have in the end. It's a little circle thing with some little standoffs to hold a metal board and an accelerometer. Notice it has a bottom part, a top part, and a little lip so that the two can merge together nicely. To begin the modeling, let's switch on over to OpenJSCAD. Here it is. I have gone to the URL, openjscad.org, and there might be some example code to start with there. If there is example code in this section, just delete it and start with something fresh. I like to start with a blank main function and a cube function here. And if you look, it's going to be very tiny, but somewhere on that screen, you'll see a tiny little cube. In OpenJSCAD, you have this left tab that can show you all your little help so that you can learn how to navigate the previewer there. The most important things to learn are the keyboard shortcuts, so when you're dragging around, you can rotate the object, and if you hold shift, you can pan the object around, and if you scroll wheel, you can zoom in and out. It's a little finicky, but you'll get the hang of it. I never do, but technically you can get the hang of it. Then on the right-hand side, above me, is the code editor. Whenever you make a change here, say I want to change from a cube to a sphere and give it a bigger size, I can type all that and then hit Shift Return. And that'll update the preview. It'll execute your code and update the preview. So that's the basic tour of OpenJSCAD. That'll get you started. Oh, I did forget one thing. When you're all done, there is a Generate STL button. Look toward the bottom of the screen there. And if you click Generate STL, there'll be a Download STL. Just click that button and you can get your file back. Now, remember also to hit Control S or Command S on a Mac to save your work often, because this is a web app and you don't want to accidentally navigate away and lose all your work. I also highly recommend copying and pasting your code into a text editor from time to time so that you don't ever lose anything. Great. So let's get to working on our enclosure. Whenever I start a new object, I like to create a new function for that object. So I'm going to create a function called Enclosure. If I could type. And let's start with that cube again. And I'm going to use the fancy version of the cube where I can specify a size. And I don't know how big I want it to be right now, honestly. So I'll just say 50 by, I don't know, 30 by 20. The dimensions here, I should say, this is important. The dimensions basically follow a 3D printer. I try to always follow a 3D printer. So your X dimension is your left and right, your Y dimension is forward and back, and your Z dimension is up and down. And all numbers that you see in here are in millimeters. So if you're an American, I'm sorry, but in the 3D world, it's best to just work in millimeters. Life is simpler that way, and we won't get into problems when uploading things to Thingiverse. Great. So let's go back. Now that I've typed in a cube here, I can go to my main function and say, instead of showing a sphere, show my enclosure. Hit Shift Return, and we can see that the screen updates with our cube. I'm going to try to zoom out a little bit. There we go. Maybe a little too much. The zoom is the trickiest part, at least if you're using a touchpad. Well, we can rotate around and see our enclosure. Now this is a solid object. If I were to hit Generate STL right now, my 3D printer would generate a solid cube. That is not what we want. What I want to do is hollow it out, create a cavity. So let's do that instead. The way I'm going to do that is to refactor a little bit. I'm going to break the enclosure into a shape and an enclosure. So I will have an enclosure shape, and I will have a cavity, which I don't know what I want yet, so I'm just going to do that. And make sure all this code is right. Let me just, it's always good to make sure the code's running before you get too fancy. So I'm going to call it enclosure shape. Okay, everything is working. Now I'm going to create the cavity. And for the cavity, I'm going to take the same enclosure shape, but scale it to be just a little bit smaller. And this will naturally create walls. So if I take an object, scale it down, subtract that scaled down version away from it, what I've done is I've hollowed out an object. And that's what I'm going to do here. So instead of returning just the enclosure shape, I'm going to use the difference function. This is where I take one object and subtract another from it. So the first object is the enclosure shape, and the thing I want to subtract from it is the cavity. So if I run that, well, you can't really tell. Because what have I done? I've hollowed it out, but it still has walls all over it. So to see if our work has worked, let's split the object into two parts, a top and a bottom. In fact, I think that I will begin with the bottom. So let's split it into just grab the bottom portion of it. So I'm going to call this the enclosure bottom. Remember, every time I want a new 3D object, I write a function for it. It's just a good habit to get into. Might be a little annoying at first, but good habit. And then the thing that I want to preview or view is this always in this main function. So instead of viewing the enclosure, I want to view just the bottom of it. And what do we need to do? First, we need to get the enclosure itself. And then what I want to do is just chop off the top. Just chop it right off. And that'll give us the bottom. So that's our subtraction operator again. We're going to start with the enclosure and chop. So here is our enclosure. And we need something called, let's call it the chopper. The chopper. Well, what should the chopper be? The chopper, I usually make these big chopping things just cubes because they're easier to work with. But in order for it to be the right size, we're going to have to know the size of the enclosure itself. So let's make these variables instead of constants there. So we'll call it the x size, the y size, and the height. And we'll make those variables. Yeah, I don't know where to put them. I'll put them at the top. X size. I forgot what I used. What did I use? 50? Y size is going to be 30. And then the height will make 20. And let's just make sure I didn't break anything. Okay, great. Let's make sure that's actually working if I change this height. Okay, great. It's shorter. Now I want to make one change. I'm going to have to scroll a little bit here so it's visible to you. By default, cubes are not centered, but I want this to be centered. And you can do that easily by just saying center true. So there, it moves to the origin. And that's just going to make all my math easier to work with. I highly recommend you work with centered cubes. Other ones are trickier to work with. Right. So let's get back to creating our chopper. Oops. So var chopper. And we're going to use a cube. And we're going to make its size to be the bigger than our enclosure. So width times 2, oops, not width, x size times 2, y size times 2, and what, height? I should have called it z size, huh? Height times 2. Great, so that is our chopper. And I want to use the difference function again. We are going to take the enclosure and chop some of it away. And run that code. Aha! And there we go. We have an enclosure with some chopping. But there are some errors with this enclosure. I think you can see we only chopped out a corner. I wanted to chop off the entire top. And that, again, is because this cube is not centered. So let's move the chopper. We're going to translate it. The function to move is called translate. And you have to give it 3 coordinates, x, y, and z, how much to move. So we're going to move minus x size, minus y size, and 0 z height. Run that code. And there we are. We have created the bottom portion of our enclosure. Pretty cool, pretty cool. Now is a great time to hit Command S to save your work so you don't lose it. I really highly recommend you remember to save because it does not autosave. Warning, it does not autosave. But this isn't quite good enough. Well, yeah, you know what? It's not good enough because we also need the top of the enclosure. So let's create a function for the enclosure top. Now here's where we're going to get really crazy. If you think about it, what is the top of the enclosure? It is the enclosure minus the bottom. So let's write it that way. We're going to return the difference, that's how we subtract things, of the enclosure minus the enclosure bottom. Remember, you need these parentheses to call functions. So we're going to take the enclosure and subtract the bottom. Let's return that from our main so that we can view it. And there it is. There's our top. Notice how it's a mirror of the bottom. Pretty neat, but what would be really useful is to be able to view both of them at the same time. If we want to combine objects, we use union. So we're going to have the enclosure top unioned with the enclosure bottom. Put that and run it, and there we have our whole box again united. but we want to be able to view into them the entire time. So let's move one of them over a little bit. We're going to translate it. That's how we move objects. And we're going to move it, I don't know, 0 minus y size 0. Ah, there. Okay. So now we can see the top of the enclosure and the bottom. And let's scale that just a tiny bit so that we can really see into it. Great. So that is our enclosure. We have a bottom and a top. And in fact, we can do even one better. Let's rotate the top so that they're both facing up. And we can use the rotate. I'll use the rotate x function. And oops, I rotated 90 degrees. I should have rotated 180 degrees. And there we can see the top and the bottom next to each other. Now they look a little bit confusing because we split it right down the middle. We split it at 0. If we choose a different split point, then the top will have a different size. So let's do bottom, I don't know. I don't know what to call this variable. Bottom size, but it's just going to be a fraction. So we'll make it 80% of the size of the object. And that means that we want to move this up. Height times, let me put that in different lines so we can read it. Height times the bottom size times 0.5, I think. Yes. Did I get that right? Do I need the 0.5? Ooh. Maybe I do need that 0.5. Okay. 80% looks too much. We'll make it 60%. Nope, still too much. Oh, I think I did do the math wrong. Okay. Height times bottom size, blah, bloop. Okay. You know what? Instead, yeah, okay. We'll do the fraction over here. There we go. So here is our basic enclosure. The bottom is on the right and the top is on the left. This is a pretty good start. I'm actually pretty happy with this. There is just one big problem with it, and that is if we were to 3D print it, the top would just slide around. What we need to do is put a lip on it so that the two snap together very nicely with a satisfying little snappy sound when you combine them. So what we need to work on next is a little lip for the box. Remember, save your work. Okay. So to make the lip, what I think we're going to do is create different thickness of walls. So let's go to our enclosure function and make the wall thickness controllable. So I'll put a parameter called thickness. Now we're parameterizing things. Then I'm going to do a little trick in JavaScript to implement a default value of 0.9. Rerun my code to make sure I didn't break anything. Great. But what that enables me to do is override the thickness. So up here, I could try a different thickness of 0.8. And we can see that the walls got thicker. If I make this closer to 1, the walls get thinner. So that is a good start. We can control the thickness of the walls. What I want to do now, I'm just going to create two different versions of the bottom. One with thin walls, one with thick walls. Move the chopper, and that'll give us, hopefully a lip. Yeah. So I'm going to call one outer. Yeah. Call it outer. And call one inner. And then whenever we want to merge things, we call union. So outer and inner. Okay, I ran the code and nothing changed. That's expected because outer and inner right now have the exact same dimensions. So let's switch inner to be an enclosure with thinner walls, 0.95. And we will move the chopper to be up a little bit, as high as we want the lip to be. So we don't move it at X, nothing there, no moving it in the Y. We want to move it in the Z, up and down. However high we want the lip to be. Let's try 3 millimeters. Run that code. Oops, maybe 3 millimeters was a bad choice. Let's see, what did I do here? Outer, inner. Good, okay. Let's just double check that the enclosure of 0.95 is working. Sometimes you have to do a little debugging of your programs to get them to work fully. So the outer, it's going to be the enclosure, yep. And this one, good. And I think the biggest problem is simply that my enclosure isn't very tall. Let's make the whole enclosure taller. Let's make it 20 tall. Let's make it, yeah, 20 tall is better. I was just running out of space, really. 30 is a little obnoxious. Let's go with 20. All right, so we're going to take this and we're going to translate it up 3 millimeters. Good. And switch these around. There we go. Little bit of futzing around, but we got our lip. I think that's one of the more challenging parts of OpenJSCAD. When things aren't working, you have to do a little bit of debugging, but just play around with the numbers a little bit, hit undo a bit, and hopefully you'll figure it out. But what's great is we have a nice configurable lip now. I could make it 2 millimeters tall. I could make it 1 millimeter tall. I could make it 5 mil. Oops, I can't make it 5 because we run out of room. But I could make it 4 millimeters tall. It's fun to make these things parametric. And that's not to say the least of which I can actually change the full size of this. I could turn it into a square. Pretty neat, huh? Because we use pretty much math everywhere. And parameters, we have a lot of control over it. We can totally change its dimensions from that. We could make it 100 to really make it giant. But here's another fun thing that we could do with it. We could totally change its shape. So let's put it back to a square. And if I go back to my enclosure shape function, just for fun, let's turn it into a cylinder. So I'm totally going to change the shape here. So a cylinder takes a radius. I'll do the x size divided by 2. And it takes a height. Yep. And then we also want to center it. So instead of a cube, let's make it a cylinder. And there we go. We have now just totally changed the shape of our enclosure and yet still kept our lip, still kept the top part, didn't have to change a whole bunch of things. I think that's my absolute favorite feature of doing work here, is that you can change your mind on what would otherwise be very critical, unchangeable decisions, and you can make those decisions changeable. You can always change your mind with OpenJSCAD. Right. So that's our basic enclosure. But we have to do a bit more work. What I want to do next is create mount points. If we look at the F7 Micro, the Meadow, the Wilderness Labs F7 Micro, we can see that it has 4 mount points and its 4 corners. For this enclosure, I'd like to be able to, screw down the Meadow down into the enclosure so it's mechanically sound. So I want to build some standoffs into the enclosure to do that. Because it's going to be a kind of new 3D object, I'm going to create a new function for it. And I'll come up here, and I'll start writing, I'm going to call it the Meadow F7. And what to start with here, I don't know. Let's just start with a cylinder. And we'll give it a radius of, I guess these will be standoffs. So the radius will be 3 millimeters, and the height will be, I don't know. How high should a standoff be? I never know. Let me fix the scrolling there. I think my head was blocking things. So yeah, I'm typing out a cylinder. Now, if I want to see it, I have to return it from main. So Meadow F7. Now, because this is JavaScript, we can only, the first return is going to return the object, and we're not going to see the rest, but that's fine. We want to focus on the Meadow now. You'll find when using OpenJSCAD that you're going to change the main function around a lot to be able to focus in on the object that you're working on at a time. So that cylinder, let's give it a name. Let's call it, it's a standoff. And we can return the standoff. Good. But that's not good enough. I want there to also be a tiny little hole in the standoff. The idea being that this should be sitting on the standoffs, and then I should be able to put a screw into the top. So whenever we want to subtract something from something else, we use the difference function. So I'm going to put this one cylinder. I have this one cylinder. And actually, I just remembered I want to center it. Always center your cylinders. It just makes life simpler. For me, at least. And I'm going to subtract another cylinder. And this cylinder is going to have a smaller radius and is going to be bigger so that I make sure it actually subtracts. There, execute the code, and there's our object, our standoff. Now, that's not actually the right inner radius there, so let's do some measuring with my handy digital calipers. And it looks like the inner diameter is 2.6 millimeters. So let's fix our code. No, I want the inner one to be 2.6, and because it's a radius, not a diameter, divided by 2. And if I execute that code, then I get the correct cylinder size. Fantastic. So that's my standoff. It's a little bit boring. I want to make it taller. So I'm going to create a variable for the height of it. And let's see, the height is 5 right now. Let's make it 8 tall. And I just need to make sure that the thing that I'm cutting out is a little bit taller. Good. So now we see that the height went up. But now, I don't need just one of these standoffs. I need 4 of them. So instead of a variable, let's turn this into a function. Remember, whenever I want an object, I create a function. So let's do that. And in JavaScript, you can have functions inside of other functions. So instead of a variable, I'm going to call standoff. Oops. And that's just because whenever you write a function, you have to make sure to return something from that function. And there we go. We still have the standoff. But I need many of them, so let's make the standoff positionable. Let's pass the x and y coordinate of it to this function, and then take whatever we made and translate it by x, y, and 0. Well, I was going to say 0, but in fact, I want to put the bottom of it at the 0 point. So I'm going to move it up by height divided by 2. And it disappeared because I need to actually pass these parameters to it. And there we go. So there is our standoff, and its bottom is now sitting on top of the grid. But because we want 4 of them, we use the union function. Whenever you want to merge things, use union. So we're going to have 1 standoff, and then some more standoffs. But to know where to put them, I need to do some measuring. So to know where to put the standoffs, I need to measure between the centers of the mount points for the meadow. So I'm going to take my handy digital calipers, do some measuring. Looks to be 68-ish millimeters. I'm going a little bit fast here. We're going to call that 68. And then I'm going to measure these ones here. I'm going to call that 18. You could probably look this up online too. But I'm going to say the X size was 68 and the Y size was 18. Cool. So now, oops, let me show you. Forgot to switch back to the code. What I did was I typed in the X size and the Y size. And now I am going to use those. So let's do X size divided by 2 because I want to center things, and Y size divided by 2. And then I don't want just one of them, but I want 4 of them. And they're going to be in alternating corners. All of that. And there it is. Look at that. 4 standoffs all ready to hold our awesome meadow device. Now, that was a lot of work for just one device mount points, but the neat thing is because we're using a programming language, we can create functions, we can parameterize everything. So let's take our meadow function and create a generic board function. And that's going to take an X size and a Y size. And then the meadow function itself simply needs to call board with the correct sizes. Board 68 and board 18. Actually, I don't even like that. Let's call it mounts. And all functions need to return something, so return mounts. And then I'm going to rename it up here also. Mounts. Okay, let's see if we broke anything. Nope, that's good. Here is the power though. I don't want to just mount the Meadow F7. I want to mount an additional device that I have, this tiny wee little accelerometer. So I'm going to measure it up, measure how far apart these mount points are on it. It looks about 15 millimeters in one dimension. And let's call it 10 in the other. So 15 by 10. So I can write function. Oh, back to the code. I can write function accelerometer, if I can type that. And I'm going to return mounts 15 and 10. And I want to view the meadow along with the accelerometer and run that. Oops. I mistyped the word mounts, mounts, and oops, I duplicated a function. So I'll switch this to mounts. Hit save, run the code, and there we have it. We have a whole set of mounts for the two devices. Well, that's not actually perfect. What we really want to do is move the accelerometer over a little bit so it's not in the way of the meadow. So let's, whenever we want to move something, we call translate. And let's see, we would need to translate it, I don't know, actually. Let's move it 20 millimeters. That almost worked. Let's try 30 millimeters. Ah, there we go. Now the two boards won't be interfering with each other, but we can mount both of them. We're putting a few too many things into the main function, so let's clean up our code a little bit. Let's create a function called parts. There we go. And then what we'll do, actually, call it all mounts. And what we'll do is we'll add those mounts to the enclosure bottom. So we'll go back to our enclosure bottom function. And we'll just add it right here, all mounts, and execute that code. All right, great. It looks like we have some issues though. Our enclosure is not nearly big enough to hold our device, but that's no problem. We can just make it bigger. We'll zoom out a bit so we have a better perspective. It looks like I'm gonna need to make it maybe, let's try 100. Oh yeah, nailed it. Perfect. So now we see the devices fit inside pretty darn nicely. And the top is still the right size. It's off to the side there. And we have our object. We just have one issue. The mount points are floating in space. They need to be brought down to merge with the bottom itself. So let's do that by moving them. And we move things using translate. And we can move them down by the height divided by 2. That did not work. Oh, I do this often. You got to make sure to put brackets when you do translate. There we go. Now they've moved down to the bottom. And we have all of our mount points in an enclosure. We have successfully created what we set out to do. Very happy with ourselves. Very happy with myself. It's always tricky coding. So let's get back to the presentation yep, okay. So I think that came out perfect. Look at that image. Look at that. Nailed it. All right. I'm just congratulating myself right now. Don't mind me. All right, so this screenshot was here just in case we completely failed, but nope, everything worked out just fine. So now let's move on to tips and tricks. There is always a little problem with doing presentations like this in that I showed you the basics and now I say, go do everything else. On Reddit, I think they call it draw the rest of the pretty aloe. So step 1, draw some circles. Step 2, yeah, the rest. So to try to help you with that, I'm going to give you some pointers that I've learned over time. And a lot of that comes down to 3D printer printability. So let's look at a few topics. Number 1 is resolution. Number 2, printability. And number 3, printer error. So resolution first. If we come back to our object here, we can see that our cylinder isn't very roundy. It's made up of a bunch of panels. We can fix that pretty easily. If we go back to our enclosure shape, there are a bunch of options here. And there's a funny option named FN. And what that is, it's the number of faces used to create the cylinder. And if I set it to a bigger number and run the code, I hope it can come out in the video, but it's a lot smoother now. The cylinder actual shape. And when you're doing larger objects, you're going to want to use more triangles to represent that object. Now the trick is sometimes you want to print at really high resolution, but it can really slow down the CAD experience. You can see OpenJSCAD slowing down from time to time. So what I like to do is create a global variable called resolution. Var resolution, and I put it right at the top of my file, like that. And the neat thing is, whenever I want to see just a lower res or faster version of my function, of my 3D object, I can lower the resolution. So here I put it to 20. Can I put it to 10? Yeah. So now our cylinder has turned into almost a stop sign. So it's really degraded. But when you're making really complex objects, sometimes it can take a while for it to process them. And so being able to control this resolution is important. And then when it comes time to print, you can just set this to some obscene high number hit enter, wait a while, and then it comes out as a nice smooth object. So it's just good to start using a global resolution variable to help out with all that stuff. I'm going to set it back to something reasonable like 50. So that's resolution. Oh, that's scrolling. You gotta, oh, that's scrolling. It's pretty wild. Watch out for that scroller. So that was resolution. Oh, let's talk about printability now. Printability comes from the fact that when you're making complex 3D objects, it may, 3D printers are good at printing some things and they're not good at printing other things. So something I like to do always is, I'm sorry I'm playing with the zoom so much, is I like to create versions of the functions that I call the print version. So I might have print enclosure top. And in the most basic sense, if everything is simple, then it's just the enclosure top. And I'll do the same thing for the enclosure bottom. Good. And then I can test these out. Print enclosure top. And print enclosure bottom. Well, it's only going to show one. It's only going to show that first print enclosure top, but that'll get things rolling. And then let me fix this code. Bottom. Good. So what I can do now is here is one object. Here is just a single top, and I can generate an STL file for it. But it's not a good file to print because it has a lot of overhang in it. It's just not a good orientation for printing. So just for printing purposes, I'll add a rotation to it to, in this case, flip it over. And there, that is a much easier object to print. So now I can hit generate STL and download it just fine. So after I've done modeling everything, I usually go through and start creating these print functions. And then when it comes time to actually print this thing, I'll just comment out code like this and export individual STL files to make all of that work. Cool. So let's leave the bottom on there. Just have one last thing to talk about, and that is printer error. So 3D printers are wonderful, but they're not always very accurate. You'll especially notice that when you're trying to create holes for, say, 3mm screws or 2mm screws or something like that. You'll find that it's going to be off by maybe 1/4 of a millimeter, or 1/10 of a millimeter, or something like that. So this is just another pro tip for, I usually create a global variable called printer error. And this is just roughly an offset that I add to radiuses whenever I have a radius. So I have a radius that maybe a piece of metal is supposed to screw into, or a hollowed out hole, something like that. So this printer error, what we have in our drawing is these hollowed out holes here, and that's where I'm going to add the printer error. So if I go all the way down to my standoff function, this cylinder here has the radius of 2.6 divided by 2. Well, all I would do is add a little bit of printer error there. And what's nice is if I get a better printer, or if something about the printer changes, I can always remove the error just by setting that to 0. Or if the printer has a ton of error, I can keep making it bigger and bigger, or whatever it takes. But maybe 0.1 I find is a decent printer error. Sometimes if I'm really good, I can get it down to 0.05, but having some kind of printer error there is always very useful. Great. So those are my pro tips. Otherwise, the biggest pro tip is read the user guide and documentation. I always hate saying read the manual, especially during a presentation, but it's true. There was a lot covered here, a lot of tricks you can learn by reading the manual. I really highly recommend it. So that's it. In summary, I'm very happy you were able to join me today and go through this. This was, let's use your programming skills to create physical objects, and in this case, enclosures, but it could be robots, it could be anything else. The best URL I have to share with you is openjscad.org. It's all pretty documented there. Just click around, start playing. It's really fun. If you want to follow more of what I do, I am at PraeClarum on Twitter. That is at PraeClarum on Twitter. And I Twitch stream from time to time, and I'm Frank Krueger on Twitch. Thank you all very much.